the screen visible or not?
Yes, sir, visible.
Okay, so today's topic is basics of electromagnetics. So we'll start from very basic like a voltage. And so what is a voltage? Anybody can tell what is a voltage? Okay, let me start. Voltage is nothing just charge accumulation. So whenever there is a charge accumulation is there, wherever there is a charge accumulation, there will be a potential difference will be developed, and that's known as nothing but a voltage, right? And because whenever there is a charge accumulation there, we have some electric field, right? Electric field all around the charge. This you have studied in your class 12th also. So because of this electric field, there will be some, you can say the strength of that field, right, around the charge. So if you suppose you place another charge in the, or you can say around this already existing charge, so there will be some force on that charge. Why? That is because of the electric field intensity or the strength of that field, usually denoted by E, electric field intensity, and its a unit is given by volt per meter, right? Because charge accumulation causes a voltage, right? And because of this voltage, there will be electric field. And this electric field is measured in terms of its intensity, that is known as electric field intensity, and it is given by volt per meter. Similar to this, when the charge moves, when the charge moves, so when charge moves, it will it will be giving you a current. So moving, if the charge is stationary, it will give you, you can say, a voltage, and if the charge is moving, then it will be give you the current, right? So when there is a rate of change of charge, we have a current. And because of this current, if you place another moving charge in this region around this current carrying wire, suppose you have a moving charge, another moving charge, so there will be again some force, and that force is because of, you might have studied Lorentz force equation, right? And that Lorentz force equation is says that when the charge is moving, then the force will be there. If the charge is not moving, then there will be no force because of the moving charge. So moving charge will only exert a force on a moving charges, and stationary charge will exert a force on the stationary charge only. So we have now the moving charge, and moving charge will be producing some current, and because of the current, you can say this is a static charge, and here you can say a moving charge, right? Moving charge. Moving charge will have a current, and because of this current, there will be strength. There will be some, you can say, energy format around this current carrying wire, and that is known as magnetic field. And the strength of this magnetic field is of magnetic field intensity, that is given by H. And because the reason, or you can say the cause of this magnetic field is current, and the unit of the current is ampere, here the cause of the electric field strength is a voltage, the unit of a voltage is volt. So here the volt per meter, so here the ampere per meter. So you can see the similarity between these two. Here the voltage is the cause, electric field is the effect. Here the cause is the current, and the effect is the magnetic field intensity. So here the unit is volt, so here it is volt per meter. Here it is ampere, so it is ampere per meter. Very similar, right? So what I mean to say is electric field and magnetic field are nothing but the energy format around the stationary charge or the moving charge, which influence other stationary charges or the moving charges respectively. So if it is a stationary charge, it will affect the stationary charge. If it is a moving charge, it will affect, and that is given by Coulomb's law. In for static case, force is given by Q E, right? Where Q is the charge, uh, and E is the electric field intensity, F is the force. And here the force is given by Lorentz force equation, Q V cross V. where B is the magnetic field. You can say density here. Actually, I will explain this later, this term later. Okay, so B is similar to H quantity. So here the force is only if the charge is moving. If velocity is zero, if the charge is not moving, then there will be no force. So the total force can be given by depending on the stationary charges and the moving charges QE U V cross V. Okay. So if the charge is stationary, there will be electric field, and that electric field will also be a stationary. It will not vary with respect to time. So it will be independent of the time. Okay. When the charge is moving without acceleration, here the condition should be without acceleration. Why without acceleration? Why I'm considering without acceleration? Without acceleration means the velocity is uniform, because acceleration is given by rate of change of velocity, right? So I'm assuming it is zero. That means the velocity is constant. It is moving with a constant velocity. If it is moving with a constant velocity, that it then in that case it will produce a magnetic field, and that magnetic field will also be static. This magnetic field will also be static. Static here means independent of time. Independent of time. It will not vary with respect to time. So there will be no change with respect to time. The strength of the magnetic field will remain constant. But if our charge is moving with acceleration, with not equal to zero, that means the non-uniform velocity. Non-uniform velocity. What here dv by dt is equal to zero. Here dv by dt will not be equal to zero. And here in this case, because we are considering uniform velocity, that means the charge is varying linearly with respect to time. Okay, so that in that case you can say that dq by dt is a constant, and dq by dt is nothing but the current. So it means this is a DC current. So basically, whenever there is a DC current, there will be electric field, and that will be a static. Okay, but when there is a AC current or your non-uniform velocity, in this case the charge is moving with some acceleration. Okay, so in this case it will have both the components, electric field, and that electric field will vary with respect to time, because the velocity is also non-uniform. It is depending on time. Okay, and it will have another component also, magnetic field, that will also be a function of time. So whenever the charge is varying with charge is moving with the acceleration, in that case it will have two components, electric field as well as magnetic field. And this is actually and both will be varying with respect to time, and this is the principle of radiation of electromagnetic waves. So electromagnetic wave, it forms electromagnetic wave. So what is electromagnetic wave? Which contains both the components, electric field as well as magnetic field, vary with respect to time, and this is the principle of radiation from the antenna. So whenever we have antenna radiates EM wave. Antenna radiates EM wave using this concept, because it contains electric field as well as magnetic field. So this is the radiation mechanism, how the antenna radiates. So basically you must have a charge with a non-uniform velocity. So or you can say the charge must be having acceleration. Okay, so when the charge is moving with the acceleration, then it will have a EM wave formation, and in this sense it will radiate. Okay, so there are a lot of similarities in electric field and magnetic field. So we'll see what are those similarities. Few of these things we have seen already. E is electric field strength given volt per meter. In magnetic field we have ampere per meter, because here the cause is voltage, right? Voltage whose unit is volt. Here we have a current whose unit is ampere, right? Ampere. So here there is a, here we have defined the intensity, right? There is another term density also. There is another term density, electric flux density. The another term is electric flux density. Density. It is represented by D and its unit is coulomb per meter square. Coulomb per meter square. Why it is coulomb per meter square? Because it is density. Density always defines per unit area or per unit volume, per unit length, like that. Okay. So this meter square is coming because of this density term, and this coulomb term is coming because of this flux. Okay. Electric flux. Electric flux is given by charge. Okay. Charge, it will have some, if you have a stationary charge here, it will have electric field of lines. Okay, electric field of lines like this if it is a positive charge. And if you measure here what is the flux passing through a particular area, that will tell you the electric flux density at that point. Okay, so flux passing per unit area, here if you consider a small area, and whatever the flux is coming out of this area will be given by this electric flux density. So that's why we denote it with the that's why its unit is coulomb per meter square, means how much charge per unit area. Okay, so similar to this quantity we have in magnetic field B. B is given by magnetic flux density. Magnetic flux density, and its unit given by Weber per meter square is coming because of Weber is coming because of the magnetic flux. Psi. Magnetic flux is denoted by psi. Okay. Here the electric flux is basically coulomb, or you can say simply a charge. Charge will tell you how much is the electric flux. Okay. So electric flux totally depends on charge. So basically whatever we are going to measure is uh, we are going to measure in terms of two things, either in terms of intensity or in terms of density, or in other sense we can say either we can measure everything in EM waves in terms of E or in terms of D. If we are going to measure in terms of intensity, we have E. If we are going to measure anything in terms of density, then we have to use D. Similarly, in magnetic field, we have to use H and B. If we are going to measure in terms of intensity, we have to use the term H. If we are measuring anything in magnetic field in terms of, we have to use the term B. Okay, so there is another term which connects these two things, intensity and density. With these terms are defined as permittivity and the permeability. It is denoted by epsilon. Epsilon is known as permittivity. Permittivity. Permittivity of the material or the medium. Okay. Permittivity of the material or medium. Okay. So epsilon is the quantity which connects these two terms, Similarly, there is another quantity in magnetic field. We have a permeability that is denoted by mu, permeability of the medium or the material, which connects these two terms, H and V, intensity and density. Both we can measure anything in terms of either E or D, because epsilon and mu are the terms which connect these two things. Okay, so what is the actual permittivity? Permittivity is nothing but the ability to hold or permit or allow the electric field in that particular medium. Okay, in particular medium. Similarly, permeability is the ability of that you can say in to allow or hold, or you can say permit the magnetic field in that medium. Okay, so It is given by epsilon equal to epsilon naught into epsilon r, where epsilon naught is the permittivity of the free space. It is for the free space, and its value is fixed. Its value is fixed 1 upon 36 pi into 10 to power 9, or you can simply write 8.854 into 10 to power minus 12, and its and here's the permeability. Permeability, which connects B and H, is the ability which tells how much magnetic field can be permitted in that medium. Okay, so it is given by mu naught into mu r, where mu naught is free space and its value is fixed, that is 4 pi into 10 to power minus 7 Henry per meter. Okay, where Henry is the unit of the inductance, because inductance always stores the energy in the form of magnetic field. And here if you see, the unit is farad per meter, and where farad is the unit of the capacitance, because capacitance saves the energy, stores the energy in the form of electric field. Okay, so that's why if you see, the units are also very similar. Here the unit is Henry per meter because inductance stores energy in the form of a magnetic field. Here the unit is Farad per meter because capacitor stores the energy in the form of electric field. So in electric field case, the unit is Farad per meter. In magnetic field case, the unit is Henry per meter. Okay, so and what about this epsilon r? Epsilon r is the relative permittivity. Relative permittivity called dielectric constant. Dielectric constant of the medium, or it depends on the medium. It varies from medium to medium. Similarly, this mu r relative permeability depends on the medium material. It varies with respect to that particular medium of material. Okay. So this you can say how these epsilon and mu relates E and D and H and B. So we'll discuss first the very basic formulas, and then I will let you know that how these are connected. So we know from your very basic point of this Q is equal to C into V, right? We know that this formula, the charge is given by the total charge is given by the capacitance into the voltage difference, that potential around that plate. So if you assume any parallel plate capacitor, how much charge is stored on that plates, that depends on the capacitance of that plates and the voltage at that plate, right? So Q, or you can say the potential difference. So Q equal to C into V. So what's the unit of Q? Q is given by Coulomb, right? Its unit is Coulomb. Its capacitance is Farad, right? Farad, and its unit is volt. Okay, so I'm just dividing it with meter per meter, right? I have divided it with meter. Simply, it's why I'm doing it. You will just get to know, because I want to derive the relationship between the D and E. Okay, so because I have divided farad per meter here also per meter, so I have to divide it with meter square, because meter into meter, then only it will become meter square, right? So I have divided to meter square. So now you recollect whose unit is coulomb per meter square. Which term denotes coulomb per meter square? This term, right? This term, that is a D. So coulomb per meter square is for the D. So here you can write the unit D. Farad per meter. If you see, farad per meter is the unit of epsilon. So this is epsilon. And volt per meter. Volt per meter is the unit of electric field intensity. This is the relation between D and E, which is connected through epsilon. So epsilon basically is the permittivity which connects the density and intensity term. Similar relation we can derive for because of our very basic things. We know the magnetic flux. The magnetic flux is given by L into I. Is also, this formula is also very similar. If you see, very similar. This is the electric flux. This is the capacitance, this is the voltage. Uh, Here the magnetic flux, here the inductance, here the current. It's very, very similar formulas. So here the unit, you can see what's the unit of magnetic flux is Weber, right? It's a Weber. Here the unit is Henry. Here the unit is ampere, right? And now I will divide this the same procedure I will follow meter meter. If I'm in the right hand side, I'm dividing meter meter, that is meter square, so it will be meter square, and whose unit is Weber per meter square. That's the density, magnetic flux density. So this is nothing but B per meter is the unit of mu, so it's mu, and ampere per meter is the unit of H. So the relation between B and H is nothing but B equal to mu H. So where mu is the permeability of the medium. Okay. So basically this epsilon mu connects DE and mu H. So after studying these basics, I will go through some basics of vector calculus, because that will also be needed while explaining the Maxwell equation. So let me tell you some basics of vector calculus. So there is one operator that is known as a del operator. This is the symbol and it is known as del. Okay. And what is del? Actually, del is nothing but it gives rate of change of any quantity with the direction of change. So what does it mean? It gives you rate of change of any space varying quantity. It must be space varying quantity. And it will give you along with the direction of change, along with magnitude, it will give you the magnitude along with the direction of change, in which particular direction you are getting. Suppose you have a temperature at a particular point, it is fixed. Okay, but if you are moving in X direction, it may be different. In Y direction, it may be different. In any other direction, the temperature may vary, right? So that depends how in which particular direction you are moving. So del is the operator which will give you the rate of change of that particular quantity in a particular direction. Basically, it is given by, we use a very simple coordinate system, that is a rectangular geometry. Then it is given by curl x ax, curl y ay, and curl is z. So it is basically a vector derivative operator, because the quantity, if you calculate del f, suppose you have a f as a temperature or any function, scalar function. Okay, so if you have any scalar function, if you have any scalar function x, y, z, so it is a function of x, y, z, then del f will be a vector quantity, right? It will be a vector quantity. You can see like this. Okay, and the unit of del will be I per meter, because it's a curl by curl x. X is nothing but per meter. It's a distance. Okay, it's a distance in x direction. It's a distance in y direction, distance in z direction. So its unit will be per meter. So it is also known as a vector derivative, a special derivative operator. It's also known as a vector special derivative operator. Okay. So this operator can be applied to a scalar quantity, and when we apply to a scalar quantity like we did in this case, then it is known as gradient of that scalar. Then it is known as a gradient of a scalar. So when we apply del to a scalar, it is known as a gradient of that particular scalar. Okay, So it is basically used to know the rate of change of space varying quantity in which direction is changing. Okay, so a gradient is nothing but a just directly apply the del to a scalar quantity. So this is the first operation that we can do using del. The second operation is uh, because del is a vector quantity, so we can also apply del to a vector. So here we can apply del to a scalar, right? And we can also apply del to a vector quantity. If we apply del to a vector quantity, we can apply del to a vector quantity in two ways, right? In two ways. Why? Because this is a vector and this is also vector. Vector and vector can be applied in two ways, either in dot form or in cross form, right? We know if there are two vector, you can multiply those two vector in two forms, a dot b or a cross b. So either in the dot product form or the cross product forms. We are going to use del dot a if a is some vector, okay, and del cross a if we have another vector a, we can apply either in the dot form or in the cross form. If we apply it in the dot form, it will give you a scalar value, and it will, if you apply in the cross form, it will give you a vector function, right? It will be a vector function, it will be a scalar function. So what this dot terms tells means, so when you apply a del to a scale vector quantity using dot, it is known as a divergence of a, divergence of a vector. It is known as a divergence of a. And when you apply a cross to a vector, it is known as curl of a. So what do you mean by this divergence of a and curl of a? Divergence of a tells suppose you have a bulb, you have a bulb, right? And the bulb is glowing. So what will happen? The intensity will be all around the bulb, and it will be coming outward. It will be coming outward, right? So when something is coming outward from a source, suppose you have a source here, you have a source here. So something is coming outward. Very basic example you can take of the charge. If you have a charge here, then what will be coming outward? The flux, electric flux. So if something is coming outward everywhere, if you see around this charge everywhere, every point, if you see, the flux will be coming out of the some closed. Suppose you take a closed sphere. If you take a closed sphere, so if there is a charge inside that sphere, what is happening? The flow of the electric flux will, okay. So in will be positive. Divergence tells you the outward flow. So if there is an outward flow, then divergence will be positive. If there is an inward flow, so instead of positive charge, suppose you have a negative charge, then in that case the flow will be inward. So electric flux will be flowing inward. So in this case, if you take a sphere, the net flow of the electric flux will be inside the sphere. Okay, so in this case, the divergence will be negative. Okay, so divergence will be negative. So if there is a no source, no sink, it is known as a sink. You can say this is a sink. So if there is a no source, no sink, so that the in that case nothing will come outward, nothing will go inside. In that case, the divergence will be zero. Okay, no source, no sink. That means divergence of that quantity will be, okay. Very important thing here to note down is uh, when you go away from this source, when you go away from this source, as you go away from this source, the strength of the flux, or you can say the field, will be decreasing, but the total area will be increasing because the radius of this is increasing. Are you getting my point? So as you go away from the source, the strength will decrease, but the area will increase. The strength will decrease, but the area will increase. What do you mean? So we can actually write the strength into area will be a constant. So if you take an example of a bulb, if you go away from the bulb, the light intensity will decrease, but the total area covered at that particular will be more. It will happen in such a way that the strength into area will always remain constant. And this constant is nothing but directly proportional to the cause of this strength. What is the cause? In this case, if you assume charge is the cause, if you assume in case of bulb, you have a cause is the bulb. Here you have a charge, so it will be directly proportional to Q. Taking an example of a charge Q, where the strength is measured in terms of D and the area is A. Okay, so if you have this charge plus Q and the electric flux will be like outward flow like this, and I'm taking a sphere, and on the sphere I am taking one small surface. Okay, and I am checking how much is the flux coming out of this surface. Suppose this surface is small area A, and the electric flux density at this particular point is D, then D dot ds will represent the small amount of flux coming out of this, but the total area is how much? You have to integrate, right? You have to integrate to calculate the total area. We have to integrate, right? So you can integrate closed surface area because it is a close. Either you can write a double integral or you can simply write make it a close. This denotes the close surface integral. S denotes the surface and this circle denotes the close. So it is a closed surface integral d dot sometimes we denote it with S because a we have used it for the vector. Okay, a we have used for the vector. Let me denote it with S simply, is equal to Q. D dot ds is equal to Q. This is the first law of electromagnetics, or you Maxwell's equations. This is known as a Gaussian law. Gaussian law in integral form. It is in integral form. Okay, there is another form that is known as a differential form or a point form that we will also study. So it is a Maxwell's first equation. So Maxwell basically did nothing. He just compiled the already basic laws in a mathematical form. So what this law says, Gaussian's law, the closed surface integral of electric flux density is equal to the charge enclosed inside that closed surface. So basically it says whatever charge is inside a closed surface, the total electric flux leaving that depends totally on the charge. Okay, so d dot ds is equal to Q. So if I say the surface d dot ds is equal to Q is correct or not, this is not, because we have not considered this surface as a closed surface. You have to consider this surface as a closed surface. Okay, if the surface is not closed, suppose this is the Q charge and you have electric flux here, and you are considering a surface here, how much flux is leaving through this closed surface not depends on this. There might be another charges here also. There may be one charge here plus Q2 here, and some flux will be because of this also, right? So in this case, this laws will not hold. Okay, it is not valid. So this law is only valid when the surface is closed. So suppose you have a charge, you assume a closed surface here around this charge, then the total flux leaving will be given by this Gaussian law. Okay, this is valid for a closed surface only, not for the open surface. This is an open surface. A closed surface, what's the difference between the closed surface and open surface? Closed surface always have some volume. Surface will not have an open surface. Open surface means a closed line, simply a closed line. Okay, and closed surface means, well, will have some volume. It will contain some volume. Okay. So this is the difference between the open surface and the similarly we have an line, simply a line, and a closed line. There is a difference. Closed line will always have an surface area. Okay, it will have always a surface. Line is simply a line, just you can say a connection of infinites, connection of infinite points simply. Okay, in where the end points are different, where end points are different, simply you can write. So you can see close lines. So this is the main difference here. So same thing is here. You have to be care while applying this Gaussian law. The Gaussian law can only be applied when the surface is closed, and this is here we have the Gaussian first law. Now we'll study about the next term, that is a vector function. Oh, sorry, this curl of a curl of a. What is a curl of a? Curl of a. We'll take another example of fan. When fan is when you switch on the fan, what will happen? The air velocity around the fan will be there in a circular fashion, right? In a circular fashion. The phenomena is very similar when you have a current carrying wire. When you have a current carrying wire, the magnetic field will be around this. Magnetic field will be around this in the circular fashion. And the strength of the magnetic field will be decreasing as you go away from the cause or from the center or from the current carrying wire. Similar to the fan, take the case of a fan. If you go away and away from the fan, what is going to happen? The air velocity is going to be decreasing, but the total length covered, or you can say the total closed line covered, the total perimeter covered will be more, right? So, this will happen in such a way that the product of these two things will remain constant. What are those two things? The strength, here the strength is magnetic field strength into the length is equal to a constant, and this constant will be directly proportional to the cause at the center. Here the strength, we have a magnetic field, and the length, we have a dl length. Suppose I am assuming small length here, small length dl. Okay, so we have a dl, and the magnetic field at, if this is h, then the total magnetic field, the total magnetic field will be the integration all over the closed line, all over the closed line. Closed line, here I have written the closed line. Okay, it's not an open line. Here again I'm writing at a closed line. C, you can say a closed curve, or simply you can remove also, simply like you can write h dl, h dot dl is equal to a constant, and that constant will be the cause at the center. That means the current. The current is at the center. Okay, so this is actually nothing but the Ampere's circuital law. H dot dl is equal to I. This is known as Ampere's circuital law, or simply Ampere's law. You can say Maxwell's fourth equation in integral form. Okay, so this is a Maxwell fourth equation in integral form. Any doubt in these two equations? So now you should ask me, sir, you have talked about del dot A and del cross A, but here there is no term appeared till now. Here I have said that the closed surface integral d dot ds equal to q. Here I have said h dot dl is equal to I, but there is no such term which coming means curl and divergence here, right? So now we will relate. this relation is actually given by two laws, that is two theorems actually. You can say those two theorems are divergence theorem and Stokes theorem. Divergence theorem says that the closed surface integral can be equated to a volume integral, can be equated to a volume integral. So this is a closed surface integral. This is a volume integral by taking its divergence. By taking its divergence. Okay. So this is the divergence theorem, because as I have said, closed surface will also have some volume. So the closed surface integral can be converted into an open integral. This is just a mathematical theorem. Maybe you have studied in your class 12 that divergence theorem, which converts surface integral into double integral into triple integral. Similarly, there is a Stokes theorem which integral in integral surface integral by taking its curl. Okay, by taking its curl. So now we will apply these two theorems in the above two cases. So if you apply the Gaussian law, what is Gaussian law says? D dot ds is equal to q, right? D dot ds is equal to q. Now I am applying this. So the left hand side will be del dot d dv equal to q. Q is the total charge. Suppose the charge is not fixed at a particular point. Suppose the charge is distributed. Suppose the charge is distributed like this uniformly with the charge density rho v. The charge is distributed with the charge density rho v. So the total charge will be how much? The volume integral of this particular value, right? So the volume integral of this rho v dv, right? Triple integral or volume integral rho v dv. So if you now equate these two equation, del dot d, the left hand side equal to right hand side, will give you now del dot d equal to rho v. And this is nothing but the divergence of electric flux density. And the divergence of electric flux density is equal to the volume charge density, okay, present inside the closed surface. Okay. Similar here, you can apply the what is Ampere circuital law? Ampere circuital law says H dot dl is equal to the current at the center passing through this surface. Okay, so that is I. But if the current is also distributed instead of suppose the current is distributed over a surface, okay, over a surface. Suppose you have a current carrying wire, right? Current carrying wire with area, some cylindrical you have. So basically a current will be distributed all over the cylinder, and the density of that current will be given by J, current per unit area. Current per unit area. J is the current density. So in that case, what you can write, you first apply the Stokes theorem to the left hand side. If you apply, it will be equal to del cross H ds is equal to what is current? Current is distributed and the density is J. So J ds. Okay, J dot ds, you can say J dot ds. So if you, now you equate these two terms, because this term is nothing but equal to I. J is the current density. The total area, if you multiply, you will get the total current, right? So del cross H equal to J. This is the Maxwell equation in the differential form. Similar, this is the Gaussian law in integral form, Maxwell differential form. For some, you also call it as a Maxwell equation in point form. Maxwell first equation in point form or differential form. Because these Maxwell equations are only valid when the charge is distributed or the current is distributed. If the charge is fixed at a particular point, it is not applicable. This law is not applicable. Okay. Similarly here, this differential form of J is only applicable when the current is distributed. Okay, so that's why it is known as a point form or the differential form. So this is the disadvantage of these two forms, means Maxwell equation in differential form. Okay. So this is all about the two Maxwell equations, Maxwell first equation, and what are other two equations? Other two equations are very. I mean, you can relate these two equation with these two equations, because if something is outward, suppose you have a electric flux, you have electric flux which is coming outward. Outward flow is there. Outward flow is there. So if it is outward flow, flowing outward from some particular point, it cannot be circular in nature. It cannot be circular. So it is not circular. Not circular. And if something is not circular, then its curl will be zero. Its curl will be zero. Similar to here, what curl represents here? The circular nature. If fan is not moving, if fan is not moving, the curl of that value will be zero. So if there is a no magnetic field, if suppose there is no current, then there will be no magnetic field. Field will be zero. Okay, so curl you can say is positive if it is anti-clockwise, negative if it is clockwise. If there is a no rotation, that means zero. Very similar to if there is an outward flow, then we say positive value divergence. If a inward flow, then we say negative value of divergence. If there is no inward outward flow, we say the value is zero. Similar here. So we know electric flux is always outward, positive to negative. It always flows like that. Positive charge to negative charge. If negative charge is not there, it will terminate at infinity. Okay, so it is not, so electric field is not circular. If it is not circular, that means del cross E must be equal to zero. So electric field intensity, the curl of the electric field intensity must be zero. This is the Maxwell's second. Maxwell's second equation. What is the Maxwell third equation? The Maxwell third equation is, because the magnetic field is circular in nature. Magnetic field is always circular in nature. It's a starting from the same point and ending at the same point. Okay, it is circular in nature. So it cannot be outward like electric field. Okay, it cannot be outward. So if it is not outward or inward, then its divergence must be zero. So del dot B must be zero. This is a Maxwell third equation. Maxwell third equation. So this is in the point form. You can apply the Stokes theorem, divergence theorem to get it in the integral form. Let me just apply the integral. If you take the in both side, you will E dot dl is equal to 0. Here you will get double integral, or you can say the closed surface integral b dot ds, because here it is divergence. You have to apply the divergence theorem. Here we will apply the Stokes theorem. Here we will apply the Stokes theorem. Here we will apply the divergence theorem. If you apply the divergence theorem, you will get this equation, Maxwell equation in integral form. You will get E dot dl is equal to 0. Okay, b dot ds is equal to 0. And this is with this we have completed the Maxwell 4 equation in static case. A static case means here I have assumed um, uh, E field, H field are static. Are static means they are not varying with respect to time. We'll continue from here in the next lecture, where we electric field, magnetic field are varying with respect to time. Just to tell you that this Maxwell's second equation is you already studied in your class 12 in the form of a KVL, Kirchhoff's voltage law, because here it is also a closed line, right? It is a closed line. So I'm saying that the electric field, if it is moving in a closed line, then its integral will be equal to zero. Its integral, it will be equal to zero. And this you have studied. What is E unit is volt per meter, and what is DL? Meter. If you cancel meter, it is nothing but V. What this integral indicates? The summation. So summation of all the voltages in a closed line is equal to zero, and this is nothing but the KCL. Okay, sorry, KVL. So Kirchhoff's voltage law. So nothing. This just Maxwell's second equation. The basic nature of the electric field is nothing but KVL. It's very simple. You all studied, right? So this is all about the Maxwell's equations in static form. Any doubts? If you have, please let me know.
Sir,
Yes.
closed surface, you said that the form volume, na?
Yes.
But if it's not, means it also form volume, but charge does not consist inside it. It also follow the uh, Gaussian law integration formula.
See, if there is a no charge, then the right hand side will become zero. Q will be zero.
Yes, sir. But open means you said if open, then
Mhm.
it is not necessary. Na open means what? Uh, it have volume,
Open
but
means
it
yes.
have volume, but it doesn't consist charge inside it. Na.
No. Open
O-
surface is different. Closed surface is different. Open
o-
surface means there is no volume. It won't have any volume. It cannot contain anything inside it. It's an open. A
okay.
plane is just an open surface. A closed box is a closed surface. Okay.
But
A
during when
close,
you
let me take an example of a cube. If you take a cube, it has six open surfaces, but one closed surface. Six open surfaces, but one closed surface. Are you getting my point?
yes, sir.
Yeah.
But the
So there are
thing is
six
that now
sides.
when
Uh-huh.
you giving us the information about Gaussian law integration form, you said that if open surface, then we couldn't use that very part. But if it is
Yes, you
closed
cannot
also,
use the
we
Gaussian law. You cannot apply a Gaussian law to an open surface.
yes, but
That will not be valid.
yeah, but close also na if it is outside the charge. Yeah, I think
Sorry?
you missed that part.
Which part? No, I didn't miss anything.
No, sir, means you didn't say that a closed surface which is outside the charge means charge is outside. It will not consist Gaussian's law integration form.
You are saying that, you are saying you have this closed surface and there is a charge q outside this. You are saying like this?
Yes, it will also not working for Gaussian's law integration formula.
So see, the closed surface, what Gaussian law is? Let me tell you. The Gaussian law is this. The closed surface integral of electric flux density is equal to the charge inside the closed surface. I have said inside. I have not said outside. Okay, if inside there is no charge, that means it is zero. Here, if you say, if you apply the Gaussian law in this case, and if you assume this as a closed surface, so in this case it will be having electric field like this, right? Electric field will be like this. It will also pass. this closed surface, right? So if you apply the Gaussian law here, the Gaussian law will be like this.
Yes, sir. Yes,
D
it is.
dot ds will be equal to 0. Why it is 0?
Charge is not inside it.
Yes.
That's
Or the alternate way you can say whatever the electric flux going inside the
will
closed
come out.
surface
Yes, sir.
is coming out. So net electric flux living through the closed surface is
Yes.
0. So you can say divergence of this D is 0. So you can say in this way also del dot D equal to 0 because there is no charge inside.
Mm.
Okay.
Yes.
But if you consider some surface, open surface here, if you consider open surface, not close, here it is close,
Yes,
here I
sir.
have
Yes, sir.
considered open. So in this case, this is not correct. This is not correct. If it is open, then D
The flux
dot
will pass
ds
through it,
will
but
have some non-zero value.
yes, sir.
Okay, and that will be some flux, electric flux, you can say E flux,
Will pass
but it
through it.
will not be equal to Q. It will have some less value than. Okay, so some
Right.
partial. Okay, because some flux is passing through this surface, some flux will be passing through here, some flux
Yes, sir.
will
Yes, sir.
be passing through here, like that. Okay, so in open surface you cannot apply the Gaussian law. That I mean to say, you cannot apply the Gaussian law is only valid for the.
Close surfaces.
Any other doubts?
Close, sir. I get it.
Okay. Okay, so if there are no doubts, you may leave the meeting. Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.